on the edges or on the edges of our simplex. Okay, this is a vector, and we call it the centroid vector of a face. And this terminology is borrowed from Fiedler. Okay, this is not ours. What is now the centroid of the simplex? If you now say that this is the UUU, the 1 vector for all of them, then you see that it's 0. So the centroid of our simplex is just the origin. And that's nice. So we take this as the origin, and all the other vectors, the S vectors, are pointing from the origin to the edges of the simplex. Another thing which is, I find cool, but rather straightforward, you can use complementary phases, meaning that a phase is basically governed by all the ones that belong to the phase, and the complement is, and I write here the complement as V with a bar, that's the complement of that. This is just this kind of an easy definition of complement, but if you fill it in the centroid, and again reminding that the 1 vector is an eigenvector of the S vector, so it disappears, then you see that the centroid here, or the centroid of a certain phase, is just pointing in the opposite direction as that of the complementary phase. In the triangle, you see it like this. If you have here now the centroid, you see the centroid is here, and this, the vector C2 is pointing in this direction, and the complement is pointing in the other direction. So this is nothing else than the well-known property that the middle lines of a triangle are all going to the center. They're all crossing in one point, and the point here is our centroid. So that's another way of looking to a geometric property on triangles, and which you can actually extend to any phases in the simplex. Okay, let me now come to the geometric representation of a graph, because this was a little bit introduction in how you represent the centroid and barycentric coordinates. It's a bit complex, I know, for the first time, but anyway. So I'm now going again to use the spectral decomposition of the Laplacian, and now I write this as these vectors Si, and the scalar product from Si over Sg, you can work it out, is nothing else than the element of my Laplacian. Okay. This means that if I have the scalar product, I can also find the norms. You can compute them, but in the figure it's more easy. If you now see again the triangle, you have the barycentric, well, the centroid, which is the origin, and each of these edges is a vector S1 and S2. Then you see that the length of S1 is nothing else than the degree. That's nice, because that has a physical representation of the graph. So the length of this vector